Once again, welcome to C++ Now. It's the 6th or 7th conference in a row now. 7th year? Is it 7th or 6th? 7th. The 7th, yeah, 7th conference. So I'm very glad that we have Dan Quinlan today here as a keynote speaker. Dan is the project lead of the ROSE compiler toolkit. Many of you might have heard of it. It's a toolkit for source-to-source transformations for different languages, mainly C++ targeted, but they do Java as well. Ooh. Are you sure you're doing Java?
We work for money.
Okay, shit. Dan got his PhD in 1993 from Colorado State. Is it State University?
Colorado? No, Colorado, University of Colorado.
University of Colorado, so right around the corner here.
That's right.
His research interests are very manifold. He's interested in anything which combines computer science with math, and his PhD was on that topic as well. Things like source-to-source transformations, DSLs, binary and source code analysis, and many more. He will talk to us today about how C++ is used in the DOE, the Department of Energy. He is working at the Lawrence Livermore National Lab, so he has a long standing insight into how DOE works and how you can get funding from DOE and all that things. And I hope to get some insights in that direction. Dan.
Thank you very much. So thank you. Is it off? That one's off? Yes. Okay. Wonderful. Thank you very much. So my name's on the slide, but in fact, actually, there are quite a few people who have contributed to different parts of this work over the years. There seems to be a bit of a ringing in the mic. Should I move this down or something? This one should be off. Okay. Maybe it's more off now than it was before. Great. Now it's really off. Maybe. Okay, so there's many people involved in work, and to a certain extent, it's a bit arrogant of me to suggest that I speak for all of DOE. In fact, I don't. I don't even speak for my own laboratory, and it's not my laboratory either. The point is that there's a lot of work within DOE, and there are different parts of DOE, and I can give you some perspective on how I see C++ having been used from the perspective of having been at two laboratories, both Los Alamos and Livermore, and been very involved in C++ work for 25 years at these different laboratories. So with that said, and I'll try and, if I get a chance, give credit to a number of the people who've contributed pieces of some of the slides that I'll be producing. So my goal is to present a little bit of an outline here, and this slide will show up again at several points during the talk to highlight the different parts of the talk that we're on at that point, obviously. And so I want to first cover a little bit of the history of C++ usage at the labs. I'll start off with a little bit about the labs. Then I'll go a little bit into the complexity associated with applications at the labs. And also algorithms. Now, this will be generally about application complexity for HPC and application and algorithm complexity for HPC, and I'll give you some specific examples. Then what I want to do is go into how the architectures have changed. Now, I know a lot of you already know about how architectures have changed, but in fact, actually, architectures are changing in a more significant way for DOE as a result of a large-scale program to develop the next exascale computer, and that represents significant changes for the lab, which are relevant for how we use languages. And then I'll talk a little bit about HPC software development. Then I'll discuss some future directions. So in general, it's sort of a balancing act that we're balancing the complexity of algorithms, the complexity of the architectures, and the complexity of the applications. Applications at the laboratories have up to about 20 developers on them, sometimes far fewer, maybe only 3. And Each laboratory has, in general, a couple different applications which more or less stand for why that laboratory is, is in business at that point. So these applications are not of some insignificant importance to the laboratories. They're the reason why the laboratories are there, and they serve a specific mission interest. So there are, in fact, many DOE laboratories, and obviously I only have perspective on 2. And these 2 laboratories where I've been, both Los Alamos and Livermore, are what's called a part of DOE is divided into 2 halves. They are the laboratories representing the defense programs. So these are more classified facilities than the open laboratories like Brookhaven, for example. Los Alamos got started in the 1940s as a result of the Manhattan Project, moving to a more secure location. A lot of interesting work got done there, and as one moved from above ground testing to underground testing to no testing, computers became an essential piece of how it is one simulated the sort of devices that were important to these labs. Livermore got started a little bit later as a result of a movement from atomic weapons to hydrogen weapons, and Edward Teller, who's the father of the hydrogen bomb, actually founded Livermore. So Livermore started in the 1950s, roughly. When I moved to Los Alamos, they were just celebrating their 50th anniversary, so this was quite interesting. Not too long ago, the 50th anniversary of Livermore was celebrated. It's the criticality of these missions that drove HPC in the early days, at least within DOE, and principally worldwide, simply because HPC was the dominant thing that was driving computing very early on. This is no longer true, however. And so in a sense, HPC is at some points living off the coattails of a lot of other things that are motivating and moving computing worldwide. So there's an increased emphasis on computing resources at the labs, and the laboratories typically have the largest computers in the world. Los Alamos and Livermore typically trade back and forth between who has the fastest computer in the world. Recently, however, this top spot was seized by the Chinese, who also have a supercomputer interest. There's been a long-term interest on performance. When I moved to the labs, the vendors would come by and tell you about how it is they had good price performance. The joke was that we didn't really care about price, we cared about performance. That was more true then than now. Things are much more driven by the economics of computing, and now performance includes both cost and power. So we're trying to do this balancing act of building machines that in fact are efficient to use and efficient to run. And we'll see a little bit about this when we talk a little bit about our types of architectures that we're going to see in the future. So there's been an evolving use of software at the labs. In the beginning, there was, of course, assembly language. About the time I arrived at Los Alamos in 1993, that was pretty much the end of the assembly language. They were no longer writing any assembly language at that point, partly because the architectures were changing so frequently. There were, of course, computer languages. 1957 represented the development of Fortran. There's many interesting stories, which I'm not going to regale you with, about those early days of Fortran. But of course, I also wasn't even a part of it because I wasn't old enough. So I know this because we support Fortran within our ROSE project. So C++ was essentially the last large general purpose language to be developed that it was of use, that has been of use within HPC and at the labs. And around 1990 was some of the first work at Los Alamos and Sandia on C++ usage and the exploration of that. So while this was happening, architectures were of course becoming more complex. We went of course from sequential machines to vector machines, which had the first level of parallelism, and then to distributed memory parallel machines. There was, of course, a debate over whether or not shared memory or distributed memory would in fact rule the day, but distributed memory machines ended up ruling the day because you could simply scale them farther. We now expect exascale computer architectures, and these are going to be quite different, driven mostly by the fact that power is very important in the design of these sort of machines. Now, let me just say here at the bottom, this is the theme of this talk. So slide 4, your program under any semantic preserving transformation is equivalent. We'll revisit that theme a couple times, and then at the end I'll ask you a question about it. But the point is that where I've been interested in this sort of work touching supercomputing is where it is libraries aren't quite good enough. In fact, you need compiler support. So I'm obviously speaking to a library-centric sort of audience, but I hope you'll agree that libraries aren't always the only solution, and they aren't always the best solution either. But where they are a solution, they should definitely be used because you shouldn't try to over-engineer a problem. So I've prepared a small time scale. It's obviously my perspective on this sort of time scale. Initial work at LANL and also at Sandia was done early 1990. There was Valoray work, which you're all familiar with. I think probably nobody really uses that. It's a part of the standard. It's a part of an ANSI standard, and it represented Sandia's attempt to support an array abstraction. It was only a one-dimensional array abstraction, unfortunately, and it represented sort of their take on how this should be addressed in the sense that they put a lot of energy into making it a standard. It's now a standard, and I'd be curious as to whether or not anybody really uses it. It has semantics which are best suited to a compiler taking advantage of them, and actually a problem in terms of performance if in fact you don't have that sort of support. There were HPC, there were multidimensional array abstractions developed in 1993 and at at Los Alamos. This was part of work that I did and several other people did. There were HPC abstractions for complex geometries around 1995. I'll be showing you some examples of this in a moment. There was a large amount of AMR work being done, and that work started in 1995 and also at LANL, but similarly at LBL as well. So there are actually multiple groups working on adaptive mesh refinement. And I'll explain what adaptive mesh refinement is. It's my example for you of how it is algorithms have become more complex over time. There was a large amount of work on array abstractions using expression templates around 1996. And there was a portable expression template library which developed around 1998 at Los Alamos. And this was very popular for a short while. And in fact, actually, I know of one application that's even still using it today. There are large projects using C++ at Livermore. In fact, all of the large projects at Livermore are using C++. So this work started around 1996 at Livermore. Interestingly enough, although the C++ work had been more dominant at Los Alamos, obviously this is my perspective on this, and in the late 90s, in fact, actually, it didn't go well, and the team left, and the laboratory went back to Fortran. So there was an interesting experiment with C++, and it didn't go well for them, and they went back to Fortran. And so Los Alamos has actually been at Fortran ever since around year 2000. They are, however, trying to move beyond that, and there's a great deal of emphasis within that laboratory to move to C++ now. It represented a very aggressive approach for Los Alamos to pursue C++ at the time, and they pursued it very aggressively. This had problems. Livermore, in contrast, had a very conservative approach. They had a couple different projects. The projects were first in C. One of the projects used C++ more aggressively, but not not too far. And in general, both these labs represent relatively conservative institutions, and Livermore, having gotten into C++ gradually, came to use it better, I think, and use it with more perspective, and in fact still uses it today. And now all of the applications at Livermore are in fact in C++. And by all, I mean the laboratory's large-scale applications. And while I've told you that they all use C++, in fact, almost uniformly within DOE, anybody using C++ is probably using something in the Fortran down below, hidden away. So these applications typically mix a few languages, but they're dominantly C++ at Livermore. Most labs are using a combination of C++ and Fortran today, but it is still the case that Fortran is used in about 70% of all DOE applications. This is mostly because there were these two halves of DOE that I referred to before. There was a large influx of funding to one of them, the DP labs, as a result of the ASCII program, and that gave them an opportunity to move to different languages. Whereas other parts of the other application groups didn't have such a large influx of money and simply kept doing things the way they had been doing it before. So there's a mix of C and C++, C++ and Fortran used today at the labs. Codes at the labs typically live 10 to 15 years. This is a long time when you consider that large-scale parallel architectures are arriving every 18 months. This has an obvious consequence in causing the laboratories to be obsessed with maintenance of these codes and very practical concerns associated with software engineering. In many cases, C++ fits this bill very well, and so it's used partly for that reason. The ability to have abstractions and then hide things behind them has been a very powerful motivation for the use of C++. Most codes are using a subset of C++, however. They don't use the full language. In fact, actually, granted, I'm speaking to an audience of Boost developers, but most people are not, except for you guys, using the full language. And most applications probably shouldn't try to use the full language. It's just not necessary. Most of the laboratory's applications operate under some restricted semantics. These restricted semantics are, in fact, never communicated through the libraries. There's no languages. There's no way to communicate that to the compiler. So as a result, there's no way to take advantage of that, unless, of course, you grab a hold of the compilation steps associated with that. And so there's been a great interest in code generation. That is to say that we wish to write in high-level abstractions, but we want to, of course, use libraries, but at certain circumstances, we want to, in fact, generate code. Now, there's a whole history of code generation, and I've laid it out here. And, of course, in the early days, there was macro processing, and that got taken way too far. And, of course, there's templates. There's expression templates. There's elaborate scripts that you can write for generating code. There's specialized tools that you can use to generate specialized code. And then there's, and I put this one more or less at the end, compiler-based code generation. Now, in a sense, all compilers are about compiler-based code generation. So in a sense, why isn't the normal compiler that we're using doing all this for us? Well, it's not, because we have rather specialized demands on the kind of code that we want to have be generated. So early on, the focus was on compilers, and that's still largely true. We want the compiler to solve all problems, but they in fact don't solve all problems for us. They're designed only to tackle the semantics of the language that they're trying to compile, and they don't allow any sort of optimization if you're in fact using a subset of that language. It's addressing the broad semantics of, or the worst case semantics of using the language in general. And since C++ is derived from C, it has a lot of constraints associated with what it can be assumed. So for example, it inherits the same properties of pointers as from C, and in general, pointers can be aliased, so as a result, you know very little about how to optimize certain parts of code as a result of not being able to do a complete alias analysis. In contrast, Fortran assumes no aliasing and has an advantage there. So these sort of differences make a difference in how much program analysis you can expect to drive from the input applications. However, if you were to program in a subset of the language that, for example, didn't use certain properties of the language. So for example, if I were to write an application that did not take advantage of pointer arithmetic, I could know much more at compile time and as a result, do more optimizations. More importantly, if I wrote my application in some abstraction, I would have the ability to leverage the semantics of that abstraction in a way that the language compiler can't. So for example, if I build an array abstraction and I endow that array abstraction with commutativity, associativity, and so on, there's no way to communicate this to the compiler. In fact, the operators that I define, overload plus, for example, on my array abstraction, could do almost anything. And in fact, the compiler is up to the mercy of the code that represents the abstraction, not the semantics of the abstraction. So the point is that there's a great opportunity to write codes in higher level abstractions, but there's a difficulty in leveraging the semantics of those abstractions in order to do optimizations. And of course, HPC is all about getting good optimizations. So I'll repeat the theme here, and that is that your program under any semantic preserving transformation is equivalent. So I've just covered a little bit about the history of DOE. I want to go on to complexity of applications and complexity of algorithms. This is an example of a truck. It's a CAD description of the truck over on the far left. And that CAD description comes out of CAD drawings, and it could be almost any sort of device that's described by a CAD drawing. And these figures are from a C++ library, which is open source, called Overture, which basically has all the abstractions for doing this sort of work, going from the CAD description to the surface grids, generation of surface grids on the CAD description, CAD surfaces, and then the growing of the three-dimensional grids over on the far left to form a basis for solving partial differential equations, in this case associated with flow, in the solution domain. Now, what's clear here is that there is quite a bit of complexity in the geometry. That complexity in the geometry translates into complexity associated with the different sorts of grids that are built in order to support solving problems on this sort of geometry. And this is an example of what's called overset grid methods. And not all HPC methods use these sort of grid techniques. I'm giving you a very narrow perspective on HPC by presenting this example. But the point is that this is a way in which one can go from complex geometries to real simulations, and there are C++ tools that are available for this. And the first version of this was in fact a Fortran-only version that was distributed as late as 1990 and maybe 1993. And that version was so complex that there were about 3 people in the world who knew how to use it. Graduate students could be thrown at that particular library and they would wilt. This was not a productive way to present these sort of abstractions, and it was not a productive way of moving this field forward. So at Los Alamos, this work was reconstructed with C++ abstractions, and it was made quite a bit more tractable and extended quite far as a result. So each one of those grids is in fact a grid object. The collection of grids is a composite grid object, and we'll go in, well, I'll show you a few more examples a little bit later. But the point is that this grid this patchwork of grids here is then embedded in a large Cartesian grid, and now we can solve flow fields associated with this. This is, let me give credit to Bill Hinshaw for, he's the author of this overture work, which is in fact worked on by several people. This is another example showing a set of city buildings. The individual buildings have been gridded up. They're then put into a large Cartesian grid. Obviously, I'm showing you a two-dimensional version of this grid, but it's of course a 3D problem. And this is important if you're trying to detect where it is if something is released, it would spread in a city. But the point is that this is showing you a little more clearly how it is the individual geometries are in fact represented, and in fact they're inserted into a Cartesian grid in order to support deriving equations on these sort of grids. This is a type of complexity that is common at the labs, that is to say to handle geometry. This is simply one way of handling geometry. There are other ways of handling geometry. Each have their advantages and disadvantages. This is actually a figure of the aorta. It's derived from MRI descriptions. And in this case, one's looking at blood flow through the aorta. In particular, that blood flow associated with a blockage shown right there. So there's simply a broad number of different sorts of applications that HPC represents, and in this particular case, I'm showing you a C++ library that has been developed over the last 20 years in its C++ form. It was, of course, developed in the Fortran form before that, but it's been developed over the last 20 years in order to support making it easier to do. This is showing you a gridded up version of a windmill. The windmills are of course huge. They're several hundred feet tall, and they're apparently very sensitive to variations in flow fields. So they in fact work best with very steady incoming flow, and the flow of downstream of a windmill will in fact be anything but steady. And so it's a problem if you have the wind blowing in a particular direction where one windmill's downstream flow behavior is affecting the upstream flow behavior of another windmill. And you can in fact break these things this way, I'm told. But the point is that these sort of applications have complex geometries. They also have complex flow fields. And these flow fields are important to understand in order to design these sort of things better. This is simply showing you a canonical example with some obvious complexity associated with turbulent flow. There's also the subject of adaptive mesh refinement. And so this is how it is. I want to talk about the algorithms becoming more complex. In this particular case, I'm showing you a very highly resolved flow associated with a shock wave on this sort of impeller. And in this particular case, we're seeing a great deal of detail in the flow field. That detail requires a great deal of grid resolution in order to support. And so what's happening is there is a coarse grid in the background, and then there is additional grids that have been added in order to support providing higher resolution around shock boundaries. The figure over here is showing you a little bit more clearly how it is there are three levels of refinement. There's the base grid, there's the green grid representing the second level of refinement. That, of course, extends into the overlapping grid as well. And then on top of that, there are red grids representing refinement over the shock boundaries. This is important in order to correctly resolve shocks. You need a lot of grid support there. But the point is that if we in fact had the whole problem have the resolution of those grids, it would be an intractable problem to solve. It would require too much memory, or it would take too long. This is an algorithmic technique in order to address simplifying HPC applications. There are in fact a number of high-level C++ abstractions that have been developed in order to support these. And so I'm showing you a deceptively simple example, a really rather trivial example from from one of the tutorial guides. Here we have an equation at the top, which we'll revisit a little bit later when I discuss how it is other tools can be used to generate the discretizations associated with that equation. There are composite grids, which represent the collections of grids, and then there is data on the grids, this concept of a grid function. And there are, of course, numerous operators that have been defined for these things. This statement looks deceptively simple. In fact, these operators are hundreds and thousands of lines of code and are simplified in numerous ways depending upon whether the grid is curvilinear coordinate grid, Cartesian grid, etc. So at this point, I've talked a little bit about the history, and I've talked a little bit about algorithm and application complexity that drive a lot of HPC work. And now what I want to do is discuss the architecture complexity. And this will hopefully be something you've never seen before. I'm sorry? By the way, feel free to ask any questions during the talk. I'm interruptible. In looking at large-scale computers, moving from 2009 to 2015, 2018, these dates have probably slipped, but the point is, in looking at the details of what are current versus future supercomputers, we can expect a number of different properties associated with them. We in fact have bounds on what we can expect. Everybody operates under the same physics, so in a sense, no one company can do a whole lot better than another company unless they're more clever. But in principle, you'll see the power requirements are going up, and this is really the requirements that we expect to have in place in order to purchase one of these machines. So 20 megawatts is the power envelope that we're looking for. Unfortunately, the requirements for a computer of this scale, and notice we're up to 1 million cores here, so this is a fairly large machine, but it's by no means clear that one can be built using today's technology at 20 megawatts, and in fact, actually, it's well known that you couldn't do that. But these are the sort of sizes that we're expecting. Now, if we extrapolate in power what we would get for the machine that we want, it would be roughly 60 megawatts. 60 megawatts would, in fact, power several small cities. I think 20 megawatts will do a nice job on a small city. But the point is, that's way too much power. Also, in 2010, one crossed the threshold where for X amount of dollars spent on a particular computer, you were expected to probably end up spending about that much on power before you decommissioned it. So these are very expensive machines, and power is important. And if we designed the machine that we want using the technology that we had today, we'd be over budget by a rather dramatic amount. And so obviously we can't build machines the way we build them today, even in the future with all of the progressions that we expect. Okay, so these are some of the different characteristics of the machines that we expect to see for a exascale machine. Obviously, we're looking at 1,000 cores per processor and roughly 1 million processors. So 1 million nodes, 1,000 cores per node. This is what we expect to see in the future. And so this shapes how it is we're designing algorithms and software moving forward. But more importantly, this is a firm design goal. Now, unfortunately, if you were to extend existing technology out for several years, the memory requirements alone would be 20 megawatts. So there's a significant problem here. Specifically, while we have constraints, some are more important than others, and there'll be a triage phase. So essentially, 20 megawatts is the upper limit. Even if it was 30, it wouldn't make that much difference. $200 million is the dollar limit, and we expect this to be delivered around 2022, something like that. We expect it to be obviously an exaflop machine, and we expect a number of things to get lost in the mix. Like I said, everything else is triage. We expect programmability to suffer. In general, programmability has suffered with every new machine that we've ever bought. They all get more complex. We expect this one to kind of get a bit more complex than typical. Now, this is a diagram showing the design envelope, or the design space associated with building an exascale machine, and I'd like to thank John Shelf for this particular figure. But the point is that the slopes of these lines may not in fact be well known, and in fact we may have to hope that there's in fact a positive region here, but if there is, then there'll be a type of machine that will be built, and it will have characteristics that are necessary in order to fit into all of these different constraints. These are the hard constraints. Now, in order to decrease power, there's a couple things you have to do, and the advantage, power is a cubic law. So if you in fact decrease a number of these things, you can save a lot on power. So the first thing to do is to lower the clock rate. This, of course, makes the cores slower, so we'll have to live with simpler cores. But as a result of lowering the clock rates, we can build simpler cores. The simpler cores take up less area, which means that they have less power leakage, and again, we end up with a more efficient sort of design. This means that we're moving from large-scale processors to much simpler processors in the future, but simply a lot more of them.
I have a question.
Sure, please.
On the previous slide, you said programmability would suffer. Could you give a practical example?
Yeah. Oh, I'm sorry. On the previous slide, which I'm trying to go to, I mentioned that programmability might suffer. And I was asked for some examples of this. I'm not a hardware design person, but when we talk to the hardware design people, they're in a rather desperate race to fit into this power budget. And so they are themselves doing their own form of triage on the sort of architectures that we have today and what has to be removed from them in order to fit into this sort of power budget. So for example, we take for granted that there are hardware-supported caches. That's a rather expensive, power-hungry solution, which we could afford in the past, but we can't afford in the future, and doesn't fit into this envelope. So you might have to program the cache yourself. And that's an example of how programmability might suffer. There are a number of others, examples like that. For example, you may have to write software that literally turns on and off different parts of the processor in order to save power. Now, this is actually not uncommon in embedded systems. And in fact, our iPhones, I should take mine out and see what time it is. Our iPhones, in fact, are designed in such a way that they're efficient in turning off different parts of the iPhone that are in fact not needed. It would be disappointing for many people if in fact developing HPC software became a little bit like writing embedded software, because laboratories don't really have that sort of expertise to do that. But we could gain that sort of expertise. So that's two examples. I'll show you what these mean in some work that we're doing in just a moment. But let me just say I encourage questions during the talk. Okay, so an additional detail is that as we lower the voltages in order to make a more power efficient system, there's a threshold for how a transistor works. You can only go so far at around 0.5 volts. If you go after that, then the machine, if you go below that, then the machine's just off. But as you approach this threshold voltage, you're in this awkward position where the reliability decreases. That is to say, the error rates go up as the voltage is reduced closer to this threshold voltage. So what this means is that for the sort of power that for the sort of low power chips that we expect to have to use for exascale computing, we're in this position where we may have to address the reliability of the hardware in a very concrete way. This is in fact another example of how it is writing the software may become more complex. So there's a number of scary ways in which software could become more complex, and this is the third one. No one produces chips in this envelope today because it'd be difficult to sell a machine that, or chips that weren't reliable. So more research is required in order to define just what level of resiliency we can introduce via software or libraries or compiler work in order to make up for the type of resiliency that we would lose associated with moving to lower power computers.
Do we expect the power or the transistors to remain the same, like MOSFET transistors? We don't expect there to be a change in our transistor technology so we reduce that?
So my understanding is no.
Could you repeat the question?
The question was, do we expect transistors to really be the same going forward? And my answer was yes. Now, I don't say that with the confidence of being a hardware designer. I just understand that from the hardware people that we work with. So it would be nice to imagine that in the time frame at which we're going to be building this, there would be new advances that we'd be able to take advantage of, but we see none of that. And in fact, all the new advances that one might take advantage of in the future are, in fact, outside of the time frame in which this machine would be built, an exascale machine would be built. So optical computing, a number of different sorts of cool advances are sort of off the table, or presumably somewhat off the table, simply because they don't fit into this time frame. You got to figure that in order to produce a machine in, let's say, 10 years, within the next 5 years, this machine needs to be really nailed down, and then it goes into production. So there's lead times associated with development of hardware that probably companies are far more familiar with than I am, but that prevents us from taking advantage of cool new ideas that we can imagine out in the future. Okay, so another thing that might happen, and this was the second thing that I referred to, is essentially gating different parts of the processors. And so I mentioned that this is commonly done for cell phones, and I'll have some slides on this a little bit later, but the point is that this contributes to making software harder to write. I thought I would put up a canonical exascale node. This has not been vetted by any vendor. It has no vendor information in it, so it's kind of safe. It's also derived from some ignorance. So the point is, you can take it with a grain of salt, but we expect to have a lot of accelerator type processors, cores, very simple low power accelerator based cores on any given exascale node. Keep in mind that there would be 1,000 cores or so on a node, so the picture is not trying to represent 1,000. There would of course be more powerful cores, so we'd have some heterogeneity in the power associated with the different cores. There'd be simpler cores, and in order to address this issue that I mentioned before about caches, we expect to see cache coherent domains. That is to say, there may be a few cores that have cache coherency between them, but there'd be only within that domain, and then there'd be many domains, and there'd be no cache coherency across domains. Now, there's a great deal of contention as to whether or not cache coherency can be supported on 1,000 cores, and there are architecture groups who argue both ways, and there are papers that are somewhat famous now that argue both ways, and I'm not going to step into that. But the point is that it's believed that it is at least fairly power intensive to support cache coherency, and also if it can be made to work, it's going to be slow, so it's going to be a problem, even if it can be supported. Simulators are a critical part of this sort of work because what we're trying to do is work with architecture groups for the first time. This is part of the exascale program called co-design, where we're literally trying to do combined software hardware co-design. Now, all these groups haven't really talked to one another before, so it's been a new experience for almost everybody to try and work together. But the point is that in trying to evaluate how it is software that we have today or software could be rewritten into tomorrow and how that software might run on future architectures, we have only simulators available to us to tell us something about this and give us feedback. So in this particular case, what we're looking at is multiple threads running on a simulator, and we're looking at the megaflops per watt in red and the power requirements in blue. And what we see is that around 14 threads, we have the most efficient execution. So this is simply one example, and there are many examples, but I'm not going to show you, of types of questions that you can answer on simulators that give you insight as to how to write software in the future. And there are, of course, more than one simulator. There's a couple different simulators. So at this point, I've covered history, application algorithm complexity, and the architecture complexity. And now what I want to do is talk a little bit about how software is developed. So, top diagram literally represents the way in which we all develop software today. It's very typical. We have people who write software. The software is represented as source code. It goes off to some vendor compiler, and then it becomes some sort of executable that we can run on hardware. And that's a common as dirt sort of way of which software is developed. And what we expect is that we're still going to have software developers. They're still going to write source code. We're still going to have vendor compilers, and we're still going to need the executable. But there's this growing gap in between. That is to say, the vendor compilers are addressing the languages specifically, but not the domains that are important to us, not all of this power requirements, not all of the resiliency, etc. And in fact, it's very difficult for them to do so. So it is convenient and somewhat self-serving for me to suggest this, that there is some step in between, and that step could be a sort of source-to-source step. Now, in fact, actually, you could just have another one of these which is bigger, better, and more tailored to your needs. That would be equivalent. But that's a little pragmatically difficult to build because you have to get the vendor to build it for you. It's in fact rather pragmatic for us to imagine taking the source code and rewriting it in a way such that we can generate new source code and feed that to the vendor compiler. And so there's a whole history of us doing this as part of this ROSE project, which I'll go into in a moment. And so that's how it fits into this sort of plan, but this is my view of this, not necessarily everybody else's. Now, let me say also that we wouldn't have to generate source code. We could generate LLVM and then connect this to LLVM, just have this take in LLVM rather than source code. So there's a number of different permutations on this. I'm giving you the simplest variety. Okay, so I wasn't going to escape, although we got to slide 27 without me mentioning it, I wasn't going to escape presenting a little bit about what it is we do. I lead the ROSE project at Livermore, and again, there are a number of people who contribute to that, both at Livermore and actually outside Livermore at different universities, Rice University, for example, several other universities. But the point is that ROSE is an infrastructure for building specialized transformation analysis and transformation tools. And so, since it's a framework for building tools, I'm describing it as ROSE down here in a big box with some of the different parts of ROSE. I'm describing your ROSE-based tool up at the top. And I'm describing how your ROSE-based tool can take in either source code or a binary executable and then operate on it, and then, if necessary, actually regenerate it back to being source code. I won't go into binary too much, and we don't do binary to source code. We do binary to binary, but the point is treating everything as source to source. Oh, thank you very much. So ROSE is an infrastructure that we've developed over the last 15 years, depending upon how you count it. And it supports a number of languages. Its purpose was to support C++, and originally C++ only. But if you work in DOE, you have to address the languages that are being developed within DOE, and so it becomes important to handle all the languages that are used uniformly in DOE, and so we've added Fortran support. So we support C, C++, and Fortran. Java is a result of some outside contracts, and we're very committed to all these languages. We also build an entire OpenMP compiler on top of this. So it's a 3.0 compliant OpenMP compiler. We also support UPC, CUDA, OpenCL, Python, and PHP, though PHP was honestly an experiment with scripting languages, which I was not very happy with. So we also support binaries, which is an interesting aspect of this. So ROSE is really supporting analysis of software generally, but C++ in particular. For binaries, we support Windows and Linux, and we support 4 different instruction sets: x86, PowerPC, ARM, and MIPS. I will get to why it is this is important for the work that we're doing, or one example of why it's important in the simulator work, because the simulators that we're using, in fact, generate MIPS code. And in fact, if you want to analyze the resource usage of an application, you can only tell so much about the source code. You have to eventually look at the binary, because the binary is the thing that actually uses the resources of the processor. So if you want to know whether the floating point unit is being used, or whether the floating point multiply is being used, so you can turn it off for power reasons, you have to be able to look at the binary. There are a large number of different sorts of analysis that are represented in ROSE. In general, you take your source code and you can represent it in different forms of analysis. These analyses are designed not to be pretty in pictures, but in fact to be used internally, and so they are typically many thousands of nodes in size and don't present well in slides. So let me take you through a short tour here. This is an example source code. This particular source code has some particular abstractions that we've implemented. There's a range object to describe indexing. There's a double array object to describe array abstraction. There's an expression involving the array objects and the indexing objects. What ROSE does is take this apart and build an abstract syntax tree. Everything is expressed in terms of the abstract syntax tree because we eventually want to be able to rewrite this and then regenerate the source code. So all the analysis happens on the abstract syntax tree, is available to you to do transformations, and if in fact you want to rewrite things, you rewrite the AST. Here what we're seeing is in fact the blue objects represented as the 2 array abstractions, the green objects representing the 2 range abstractions, and here what we're seeing is the expression representing the structure of this. ROSE is representing an IR at a very high level, identical to the grammar, because it's intended to be for source to source.
Question.
Yes?
So, does your abstract syntax, does it dig into the range and double array classes, or does it just represent the entire abstraction double array factor right there?
Well, it would only represent the abstractions. It wouldn't dig into the abstractions. I'm sorry. I'm supposed to repeat the question. I'm sorry. The question was, does the AST dig into the index and double array abstraction in order to present any details about it? And the answer is no, because that doesn't appear in the source code. It doesn't appear. If it appeared in the header files, for example, then the answer would be yes. But if it doesn't appear in the source code and it appears in a library that you link to, then no, because the AST represents the structure of the source code by definition. ROSE has an object-oriented design. It's written in C++. Every IR node is in fact a class. Here we see the class representing basic block. The basic block contains a variable declaration, a expression statement, a return statement. The return statement has an expression. so like return 0. This is the AST is a connected collection of objects, and you can traverse this with numerous tools that are in rows, and you can do transformations on it. The whole point is that this is an AST that's meant to be transformed, and it's designed to be transformed, and it's written at the level of the grammar. So you can pretty much open up Appendix B in Strostrup's book on the grammar of C++ and find a representative class for everything that's in there. There's, in a sense, some limited degree of flexibility to be innovative, but there's not a whole lot. We represent an AST which is constructed from the EDG AST, and so as a result we end up with a type-checked AST that is openly public and can be distributed, and ROSE is itself a BSD released open source tool. We have a commercial license for EDG, which means that you can go build tools and sell them if you want based on ROSE. We're not just for research use only. All details of what functions are being called is all resolved. That's all part of the type evaluation. So similarly, when we go back to generate code, we generate all of the name qualification necessary. There's analysis in order to figure out what that is. So for example, after you've done transformations, name qualification issues may have changed because things moved to different places. This is all recomputed from scratch. I mentioned before we had an OpenMP compiler. This just simply shows you the size of some of the projects. This is a significant piece of work over several years. This OpenMP compiler is again an example of how it is. A library wouldn't be enough. A compiler sort of solution is what you need in order to support OpenMP. And the OpenMP compiler that we've produced is in fact very competitive with the existing OpenMP compilers out there. I mentioned before resiliency. Resiliency is an important aspect of moving to exascale machines. You could, in fact, have this change how you write your software, but we'd like to not have that happen. And in fact, if that were to happen, that would be a very ugly thing to have happen to people's source code. So in this case, what we're showing is, in fact, an implementation of what's called triple modular redundancy as a compiler transformation. And this sort of work is done at a very, very fine grain, where you wouldn't want to do it by hand, but in fact, it might be quite reasonable to have the compiler do it for you. Usually people don't get too upset about the compiler doing things for them. In this particular case, we're taking the code over here, and we're expanding it out to this code over here. We're doing 3 times the amount of work, and then we're checking the results at the end, and then we're arbitrating the results if in fact they're different. Now, because this is done at such a very fine level of granularity, we accumulate no state associated with having gotten a wrong answer or based on a wrong answer. As a result, we don't have to worry about rolling back to a previously safe position in the code before the error happened. The cost of this is in fact surprisingly low. You'd think it might cost 3 times as much, but in fact that's not true. It costs about 3 to 40% more to do this. And the reason why is because what really costs you a lot is bringing in data from memory, not doing floating point operations on it. And if in fact, once you've brought the data into memory, you can do a lot of floating point operations practically for free in the amount of time that it takes to go get the next part. So that's why we see about 3% degradation in performance. Where we see 40%, it's because it's a computationally bound algorithm, and simply you're not waiting that much on memory. Yes?
So, take a source compiler, generate this, then push that to the main compiler. How do you prevent the main compiler just
Optimizing it away.
optimizing it out?
Yeah. So that's a, oh yes, I'm sorry. I'm asked to repeat the question. How do we make sure that the compiler doesn't optimize, the vendor compiler doesn't optimize away our cool effort to reproduce the work 3 times? That's the subject of the paper, which this is a basis on. So in a sense, I probably won't go into that too much detail here, but there are ways to essentially make the ability of the vendor compiler depend upon a pointer analysis, which it can't do well as a basis for whether or not it can figure this out. And that's the technique in brief.
Another question, sorry.
Sure.
How do you debug these transfer code?
Well, you, the user, only writes this code over here. Oh, how do you debug? Thank you very much for reminding me. At every time. The user only writes this part over here. So in a sense, the user has to, it's helpful if the user actually starts with something that's already debugged. And then you can turn on this option in the compiler. I suppose, really, the user wouldn't see anything differently. However, if your user wanted to look at this intermediate code that was generated and debug it, they could do so. So you could get either one of these. But obviously, this is more complex than that. The whole point is that the compiler generated it for you. It's always the case that whoever's cooking up the cool magic compiler transformation has the responsibility to debug it. And where it is they don't do their job, it's very difficult for the user to turn around and fix that. Yes?
How does the user know where to apply the fragments in order to optimize properly?
Okay. How does the user know where to apply the pragmas? It's the first time I got that one before being reminded. Don't have a good answer for you there. The user is expected to understand his code. You could apply it globally, but we've decided that a global application of this technique is probably a bit overkill. Probably we're only interested in critical sections of the code. So we allow the user to specify the critical section of the code. Since this is early work, this could be redone in a number of different ways. One could ultimately derive this from other work that we're interested in doing, which is essentially a static analysis of the sensitivity of the code to errors, but that has not been completed yet. Ultimately, that would be my better answer. Another example of where it is the compiler is useful to generate code for you is when you move to GPUs. Here we have a very simple code up at top, but in fact we have to generate the GPU code, and this is just a small part of the GPU code. There's also all of the code which marshals the data back and forth to the GPU memory, which I'm not showing here. The whole point is that this is difficult to embed into a library because it depends upon numerous types of analysis that you have to be able to do. So this is another example of types of code generation that I'm talking about. In this particular case, in recent work that was actually just sent off to the OpenMP conference last Friday, what we're demonstrating is very similar performance to the best. So this is the green line is the ROSE heterogeneous OpenMP version of ACC, and we're demonstrating very similar performance to the HMPP OpenMP, which is a proprietary implementation. So we make this available open source as a basis for supporting research. Yes?
On this previous slide, was this purely OpenMP or was it a mix of MPI?
No, there was no MPI. Oh, I'm sorry. I was so good last time. The question was, are these performance results a mix of OpenMP and MPI? And the answer is no. This is just MPI. This is just OpenMP and a new accelerator specification, which will come out in OpenMP 4.0, we expect. And this is an implementation of that work, or of that standard. Yes?
This is not actually using the accelerator. It's the ACC.
Well, there's two versions of it, actually. So the point from the knowledgeable person in the back was that I was mixing up the OpenMP accelerator standard and the OpenACC, and he's absolutely correct on this slide. We do have both of these implemented, and I was sort of talking broadly about both of them, but only showing one slide of one of the results. Thank you very much for clarifying. Energy management is an important part of exascale computing, And either you can manage that, manage the power yourself and the software you write, or you can expect this to be done for you. Again, it's kind of a hard thing to imagine a library doing for you. And so the compiler is in fact an appropriate place to consider doing some of this work. The compiler has to in fact do an analysis of the code to determine resource usage. And as I mentioned before, because resource usage can be very difficult to discern from source code, one might have to look at the binary. And so we support MIPS analysis of MIPS binaries as part of our binary analysis work in ROSE. And we do that in order to support this particular work. Specifically, the code is compiled to a MIPS binary so that it can run on the simulator, and we can intervene and look at the MIPS binary in order to determine resource usage within different parts of the code, and then recompile the code with different instructions in order to turn on and off different properties of the proposed hardware that's representing this represented by this simulator. Yes.
Have you been working or have you been interested in the interaction between compiler and runtime systems? Because I believe, especially on exascale, it gets more and more important to do all these things at runtime and based on runtime decisions and not based on static compile decisions.
You might be right, but the answer is no. The question was, sorry, the question was, have we looked at runtime ways of doing this? And I'll get to that slide in a moment. But in some of this initial work, it would be inappropriate to use static analysis of binaries if in fact you were trying to make runtime decisions. Thank you very much. So, so the answer is no, we're not that far along, but I have a slide specifically to dynamic analysis in a moment. I'm going to skip through this a bit. This is a little bit about the Power API that's been designed as a result of working with UIUC and Livermore in order to control the simulator. Let's see. This is some results on software managed caches, specifically in implementing software managed caches, which is part of Sade's work at Ohio State University. What's been done is essentially an evaluation of the energy improvement as a result of managing the caches through software. And so this gives you some hard numbers, granted hard numbers derived from a simulator, and one always has to be suspicious about power numbers derived from simulators, but we believe that they are relative to the simulator reasonable. They may not, the actual net values may in fact not represent the future hardware, but they are relative to one another. So this is looking at how it is different aspects of the cache behavior have been improved as a result of moving to a software managed cache. This starts to get a little bit to the runtime issue. One of the things we can detect is amount of parallelism at runtime being used, and this is motivated work to turn on and off cores. So here what we're doing is looking at an execution where we've been able to detect that there was a large serial region of the code, and as a result lower the power from here to here and save power as a result of turning off cores. This is in fact a look at the multigrid code, looking at how it is for very fine, I'm not going to explain the multigrid algorithm, but it's a very dynamic behavior, has a very dynamic behavior in how it is. It uses resources, and so what we're seeing is essentially the red areas representing computation and power usage, and the black areas representing the opportunities to shut down certain numbers of cores in order to improve the power usage. There's a lot of different analysis in ROSE. I've touched on only a few tools. There's auto-parallelization tools that we've built that use a lot of analysis within ROSE. I've tried to structure this talk so that I wasn't talking about program analysis, but talking about examples of tools that, of course, use program analysis. This is, in fact, a specific capability within ROSE to look at path feasibility using SMT solvers. And This work using SMT solvers represents aspects of rows that are more focused on verification. And here what we're doing is we're literally forming from a simple equation the logic equations representing that equivalent code. And those logic equations can be fed to a SMT solver, which is essentially a more sophisticated form of SAT solver, which proves satisfiability, which in short really means says whether or not it's true or false. So what we're detecting here is that this branch could never be taken, this branch is always taken. So that's an example of a type of analysis that you can do. And this sort of work has more use to us also in binary analysis, but I wasn't going to go into that. Yes, it can be. Sorry. Isn't SAT NP complete? Couldn't that be very expensive? Yes to both questions. In practice, the computational work is more like order n cubed as opposed to NP complete. That's a practical comment about how it appears in reality, not about how the worst case could occur. These sort of problems get very large. They could be very expensive. We're in fact very interested in parallel techniques to handle this, and we have large resources at the lab, so in a sense, we love problems that are very expensive. This is a simple example program as part of the CodeThorn verification tool, which is going to be released next month and which won an award last year. This is a very simple little input program. A distinctive part of this input program is that it's an infinite program. It has a while, so it's while true. And this is an analysis of this sort of infinite length programs is a different sort of area of verification. And so this specialized tool had to be developed in order to support this. And it's very relevant to firmware analysis. So we're actually quite interested in firmware analysis. So the opportunities to work on that would be of great interest to us. And this is some of the verification work that's been done. This generates a state diagram which represents the symbolic state of the program. And an analysis of this is what helps one do the verification. This is obviously for a very small program. For a 200,000 line program, one generates about 21,000 states, and it becomes much larger. But the point is that I've just shown you sort of the breadth of analysis and different sort of tools, but I've by no means been complete. So at this point, what I've done is I've covered a little bit of history, a little bit about complexity, and covered a little bit about the source-to-source translation and as a mechanism for how we're addressing complexity. I've introduced rows, and I've provided some examples of both analysis and some specific tools. So now, the last little part of the talk. This is a slide I put up earlier. One of the things that we're very interested in is ways of extending existing languages. So I know you must shudder at the thought of us coming along and trying to extend C++ in any particular way. Nonetheless, that's actually where we're going with some of this work. And I'll get to that in a moment. But the point is that this sort of mathematical representation is best represented at a higher level than actual source code. So in a sense, what we're experimenting with is representing this in Maple, having Maple generate the code, do all the symbolic simplification of the code necessary for it to be optimized on different sorts of grids, curvilinear coordinate grids, rectangular coordinate grids. This generates thousands of lines of code, tens of thousands of lines of code. It's a rather difficult thing to put into place, but the point is that those are the best tools for doing this. It's true that compilers have algebraic simplification capabilities to some extent, but none as powerful as what one gets in specialized tools. And so using specialized tool to generate code is in fact one of the future directions of our work. Now I'm going to end with a description of domain-specific languages. We have a large project within DOE which is funded across Livermore, Rice, a large MIT, a large number of universities, OSU. I don't want to leave anybody out, but I know I'm leaving out quite a few. But the point is that There's a large group of people working on DSL technology, and essentially what DSLs represent are a way to capture expert knowledge about application domains. And we're interested in two types of DSLs. Embedded DSLs, the kind where you write an abstraction in C++, and then you decide that abstraction, although supported by a library, may warrant specialized compiler support, and so you provide that, and that becomes an embedded DSL. And also syntax extended DSLs, more general DSLs, so that one can actually extend the language in a more obvious way by extending the syntax. I won't go into too much of this detail, but the point is we're developing really what is the infrastructure for making it easy to build DSLs. And so that's the emphasis within this project. We're, of course, going to be demonstrating this in a number of ways. We have a way of parsing this. It applies to both C++ and Fortran. And this is, of course, the contributions of many people. Obviously not myself, not just myself. There's a part of it called Rosebud, which is the front end part. Oh, I'm sorry. Yes.
How does it relate to technology like Scala?
Oh, how does this relate to Scala? I don't think I'd be able to do justice to that answer to that question. Why don't we talk about it afterwards? So Rosebud is a tool for describing the plugins, and it addresses the front-end issues associated with parsing, and we're using SDF grammars in order to parse both the new language, which represents the DSL, and then we're parsing this into separate languages which represent the base language and the extension, and then we're using a conventional front end, such as what's in Rose, in order to handle the C++, for example. So this sort of describes the two-phase parsing. The DSL parser would generate two codes. One would be the host language, which would be fed to a proper compiler, and another one would just process the DSL part. The idea is that this is smaller, and the ASTs would be merged at the end, and then analysis would take place. Okay, so this is the summary slide. This is the summary slide. So I'm at the end. I've got one more acknowledgement slide. Basically, C++ has had significant usage within DOE. It's growing all the time. And, but there is an interesting, so it's exclusively used for all of the applications at Livermore, all the large applications. It is interesting to us within HPC that C++ and C still don't have multidimensional arrays, and this is such an attractive feature. Fortran, of course, had it for forever. So this is the one thing I would like to give to you as a possible addition to C++ that would make it more attractive for HPC. And finally, we're addressing in our research how to handle problems that are really not a part of the language and not addressed by the compiler support within the language by essentially addressing code generation technologies. Yes?
I'm sorry, what do you mean by lack of multidimensional arrays? I mean, you do have array types with multiple dimensions.
Yeah, it's not the same thing.
So what do you mean?
Oh, I'm sorry. What do I mean by multidimensional arrays? Because you can, of course, have a multidimensional array in C, and you can statically declare that as a type. And this is, in fact, a rather awkward level of support to have, and it's really not good enough for HPC work.
So what do you need?
What do we need? Well, why don't we talk about that offline? Because I'm kind of running out of time here, and I want to get to the last line. So the theme of this talk was your program under any semantic preserving transformation is equivalent. And so my question for the audience is, why do we call our project Rose? There you go. That's right. Okay. The rose by any other name would smell as sweet. It's from Shakespeare. That's the answer. Now, Shakespeare wasn't quite geeky enough to say, you know, a program under any semantic preserving transformation is equivalent. But he should have for this audience, or for me. So there's a lot of different groups that we work with. This is the last slide. Rose won an R&D 100 award in 2009. CodeThorn won a verification award last year. It's used as a basis for a lot of different graduate courses at different universities. Different companies are building products based on Rose because it has a BSD license, and we have a commercial license for EDG, so as a result, you can go do this. You don't have to tell us about it or anything like that. It's not just for research only. Rose is released at the rosecompiler.org website, and it's the top download for the SciDec within DOE. So that's the end of my talk. Thank you very much.
So he deserves an answer to his question. What would I like? And
in fact, we'd like to have arrays represented much the way they are in Fortran, with support for indexing, array sort of abstractions. But the history of this sort of array abstractions is that they're very difficult to support in libraries. You can get the functionality that you want, but you can't get the performance that you need. And this is a problem because of the types of architectures that we have to run on, where you in fact want to be able to do analysis in order to collapse loops, do what's called loop fusion, and this is very difficult to support. I think it's really quite impossible to support in a library. So you can get the functionality you want out of libraries, you just can't get the performance unless it's part of the language. Then it could be optimized by the compiler.
Could this be something that's supported by you sort of showed that graph where it has a separate EDSL compiler?
Yes, and we've done that. We've done exactly that. Oh, sorry. Could what I just suggested as a solution be addressed as essentially an EDSL compiler? And the answer is yes. We've gone off and done that. However, as popular as we wish to be, we're just not popular enough that people will go and use abstractions that have a compiler support if we have to provide, if they only have a sole source from us in order to use it. So it's just not. I think it really deserves to be a part of the language more than supported by one group at Livermore. Yes.
So Intel has an extension to its compiler, right? It's called the Intel Array Potential.
Yes.
What's your feeling about that?
Intel has a extension to their compiler called the Array extension, and what do I think about that? That was the question. Actually, I think it's quite lovely. The problem is that it's outside the standard. They just went and implemented it as an extension for their compiler. No other compiler will support it unless it is an extension. And something along those lines is, in fact, what's really needed. And it supports vectorization and things like that. It gives one easier access to vectorization. So I think it's a wonderful idea. The problem is that if they do it or we do it, it's still outside the language. And people, keep in mind, labs are very conservative. They want to use the standard languages. Yes?
Well, what if you just have a normal EDSL, which is written so it will run on any compiler, and your special EDSL recognizer will just optimize it?
Right. So the question was, what if we had the support for the EDSL and then separately a EDSL compiler that would optimize it? So that way it could run, but it could also be optimized separately. Unfortunately, if it doesn't run optimized, it almost doesn't count. So in a sense, that doesn't seem to have been a good enough solution for groups that we're aware of. Although it does seem kind of reasonable. And it's a compromise. Yes?
Why analyze MIPS assembly? How accurate is a representation of modern architecture?
Oh, the reason why we analyze MIPS is because the simulators that we're using generate MIPS code and then run MIPS executables. And so in order to tie our work to the simulators, such as the resource usage, we need to handle MIPS. So we added MIPS instruction support to Rose just for that reason. But you're right, it's not a very modern architecture. Yes?
So there's nothing that says that a standard library has to be implemented in standard C++. In fact, much of the standard library can't implement standard C++. So have you thought about proposing a library that has additional prose restrictions that allow these optimizations that don't care about that can just implement it in the same C++ and have slow performance. But
So-
with your compiler, you can implement it with forensics or however to get the performance.
So, okay, boy, that's a long question to repeat, though. Let me summarize it, and you can tell me if I'm even close. Why couldn't we provide libraries and that had a certain level of semantic information that compilers could take advantage of if they chose to take advantage of it, and some compilers could choose not to, but others could, and provide a more optimized implementation? I would say that Valoray is, in fact, a wonderful example of that. It has semantics that are really best exploited by a compiler, but in fact, no compiler goes and optimizes Valoray because nobody really uses it, because it doesn't get good performance. So in a sense, there's a chicken and egg process here. I think in general, there are other examples. So for example, we've looked at parallel STL and compiler support for that. It's difficult to support as a library, but in fact, parallelization over containers, STL containers, is quite doable, and we've published papers on essentially what to do in order to make that, in order to make that work, and demonstrated performance examples, et cetera. And you can extend this to operations on user-defined data structures like trees, how to parallelize operations on trees. And it's a user-defined data structure, and you simply annotate the data structure with semantics that a compiler could take advantage of. I think all this is sort of a one-off implementation and yet to become sort of a standard way of approaching things, unfortunately. So we can go do it, but it kind of doesn't count because we're just one group.
Well, we're running out of time. Perhaps one question, Michael?
First, answer your question. Vectorization is being proposed in C++ in the array notation that you talked about, and it also is which you probably know, right? More interestingly, I actually want to ask a question about lowest level mode usage. Do you find C++ slow in your usage? Do you care about things like better aliasing, better restricting, things like that? And then Paul, the second question, do you use C++ 11, and which part of it?
Okay, so two questions. One, from a Livermore perspective, are we happy with the use of C++? Is it fast enough? Yeah. I'll remind you, I don't speak for the whole lab. And I'll say that I think, judging from how people have voted with their feet, yes, it is fast enough. I would say that the issues that make a difference are probably more design issues, not language issues. And so I think we're finally at that stage where we're looking at the right sort of problems and not obsessing about the language details. That having been said, there are many groups that dip down into Fortran in order to address the lower level performance issues that are in fact an issue because of aliasing assumptions in C++ that you don't get in Fortran. The last part of the question was specific to, is C++ 11 being used? I would say that there are some groups that are in fact very interested in using C++ 11. And not to torture you, but they're actually trying to torture IBM in order to get them to support it. And IBM says, well, you guys are the only ones who have asked for it. So it's sort of an interesting case, but that wasn't...
It is me, actually.
Well, okay, but since this is televised, I would say that wasn't meant for you. So there are some groups who see a significant advantage in using lambda functions as a way to encapsulate some of the parallelism at a high level for loops, and they've literally proposed innovative uses of C++ 11 features that, if used by the application groups, would then insulate them from a number of different sort of architecture changes down below or in the future. So it is of interest, but it's not uniformly seen as being important. It's just being seen by some groups as being more important.
Okay. Thanks again, Dan.
Thank you very much.